last thing that I want to go over is metric prefixes. And they have a really good table in the, actually, I can just show you the table, honestly. I forgot that I don't have to just stay on the, I don't have to just stay on the whiteboard. So I'm going to screen share, stop share really quickly, share screen right here. So the metric prefixes tell you, instead of writing down say 5 billion meters and then writing down all the different zeros and stuff like that, instead you can write down gigameters, which is 10 to the 9th meters. So if you're talking about thousands of kilometers or thousands of meters, then you would be talking about lengths of kilometers. So basically, what all of these do is, instead of having talking about base units or something like that, you can convert to these different units where the prefix in front of them, like kilo, mega, or giga, if you're talking about bytes, tell you how many of the base units, or not the base units, but the more fundamental units you're talking about. So kilobytes would be thousands of bytes, megabytes would be millions of bytes, or 10 to the 6 bytes, and gigabytes would be 10 to the 9th bytes. Or if you're talking about, say, really small distances and you don't want to say like 1/10,000th of a meter, you can talk about millimeters or centimeters or decimeters, which are 10 to the -3 meters, 10 to the -2 meters, or 10 to the -1 meter, respectively. So while we're on this, hopefully that was pretty self-explanatory, but you don't generally, when you're doing calculations, instead of dealing with kilometers or gigameters or anything like that, what you're going to want to do is make sure that all of your units are the same unit. So if you're doing calculations with grams and kilograms in the same calculation, then you're going to want to just a second. You're going to want to convert from kilograms to the grams. So, or from kilograms to megagrams, if that's what you're doing. So 10 to the 3rd kilograms is going to be 10 to the 3rd times 10 to the 3rd grams, because each gram is going to be each kilogram is going to be equal to 1,000 grams. So it's 10 to the 3rd times 10 to the 3rd grams, because each 10 to the 3rd kilograms is going to be or each of the kilograms is going to be equal to 10 to the third grams, like I just said. So you're going to multiply the two of them to get 10 to the 6 grams. So if you're doing calculations, then I would generally use keep it as 10 to the 6 grams rather than doing what they do and writing it down as megagrams. But generally, this is just a conversion factor. You can use 10 to the 6 grams, or you can use megagrams, or you can use 10 to the third kilograms, but they're all just going to be referring to the same amount of mass. And yeah, so did that explanation, that was kind of a basic explanation, but did that all make sense?
Yes, Professor.
Yeah, awesome. So while we're talking about metric prefixes, we're going to talk about orders of magnitude. So in that last slide, you saw that each prefix referred to some 10 to the n power. So giga referred to 10 to the 9th power, centa referred to 10 to the -2 power. And what these powers of 10 are the orders of magnitude. So the order of magnitude is what power of 10 is closest to the number that you're looking at. So the way that you find that is by taking, so 10 to the x equals whatever number you're looking at, right? Let's, instead of calling this n, let's call this m. So m is just going to refer to the number you're looking at. Or actually, we can call this big N. So 10 to the x is going to be the number you're looking at. And in order to find what this x is and to find the order of magnitude, you take log base 10 to the x, which is equal to log base 10 of n. So x equals log base 10 of n. And the order of magnitude is the nearest value, the nearest whole value that this value is going to give you. So for 800, x is going to be approximately 2.903, because this is equal to log base 10 of 800. So the order of magnitude is 10 to the third because it rounds up to the nearest order of magnitude. For n equals 450, x is equal to log 10 of 450, which is approximately 2.653. So it also has an order of magnitude 10 to the third, even though 450 is significantly closer to 100 than it is to 1,000. Numerically, it is logarithmically closer to 10 to the third than it is 10 to the second. And then the last example that they go to is n equals 250. In that case, x is log base 10 of 250, which is approximately 2.397. So the order of magnitude is going to be 10 squared in this case. So that's going to be their definition of order of magnitude, but the you can also kind of just eyeball it from scientific notation. So scientific notation is when you have some leading number, which I'm going to call A, times ten to the nth power. So scientific notation just tells you how much. Oh, this is kind of messy. I'm going to fix that. It tells you generally how much how many zeros are out front, how many places over the first digit's going to be. So for example, if you have 2 centimeters, or not, let's not do centimeters, 200 meters, that's going to be equal to 2 times 10 to the second meter. And then if you have 220 meters, that is equal to 2.2 times 10 to the second meters. So what you're always going to have is you're going to have one digit before the decimal place, and then whatever is to the right of that digit is going to be to the right of the decimal place. So 220 meters becomes 2.2 times 10 to the second meters, instead of just being 2.22 times 10 to the first meters, because you only have that one digit to the left of the decimal place, because it's telling you how many digits, how many zeros over the most fundamental, the biggest digit is going to be. That's basically the point of scientific notation. So if you're finding order of magnitude again, you're going to want to do log base 10 of the number, which is equal to log base 10 of a times 10 to the little n, where little n is always going to be an integer, right? Which is equal to log 10 of a plus log 10 of 10 to the little n, which is a property of logarithms. Log of x times y equals log of x plus log of y. Okay, so this is going to be equal to log base 10 of a plus n. So basically, whether it rounds up or down is going to be dependent on this log base 10 of a. So if log 10 of a is greater than or equal to 0.5, then it's going to round up. And if it's less than 0.5, it rounds down. So if it rounds up, the order of magnitude is going to be equal to 10 to the n plus 1. And if it rounds down, it's going to be equal to 10 to the n. So basically, this just gives us an easy way to tell whether or not it's going to round up or down based on whether or not log base 10 of a is the number out front is greater than 0.5 or is less than 0.5. So that tells it's going to tell you whether it's going to round up or not depending on the value of the number up front. And because you probably don't have logarithms memorized, especially log base 10, what you can do is take 10 to the log base 10 of a is greater than or equal to 0.5 or is less than 0.5 or 10 to the 0.5 rather. So you just take both of these values and raise them to the 10. So a is greater than or equal to 10 to the 0.5 or less than 10 to the 0.5 for rounding up or down. So it's going to be greater than or equal to approximately 3.16. So this is what we saw in the when we were doing those examples earlier, right? Because 10 to the 0.5, 3.16, When we had the logarithm of 450, even though it was less than 500, it was still greater than 3.16. Therefore, it got rounded up to 10 to the third power. And when we were talking about 250, which was less than 3.16 times 10 to the second power, then it got rounded down to 10 to the second power because it was less than this value. So whatever the leading value is, if it's greater than or equal to or less than about 3.16, that's going to tell you the order of magnitude of the value. And then I'm going to switch over again to the textbook, just because we were talking about order of magnitude already. I am going to share the screen to the textbook again. Okay, come on, cooperate. And this is going to tell you the order of magnitude, the scientific notation for several types of different length, mass, or time scales. So we look at 10 to the negative 15 meters is about the diameter of a proton. 10 to the negative 14 meters is diameter of a large nucleus. So it's about 10 times as big as the diameter of a proton, which kind of makes sense because it's made up of a bunch of different protons. And 10 to the negative 10 meters is the diameter of a hydrogen atom. So a hydrogen atom is just a electron orbiting around a proton. I don't even think it has a neutron involved. So in this case, 10 to the negative 10 is 10 to the fifth, so 10,000 times the diameter of the nucleus is going to be the diameter of the hydrogen atom, not 10,000, 100,000. So 10 to the 0 meters is the height of a 4-year-old child, so that's 1 meter. 10 squared is the length of a football field, 10 to the 7th diameter of Earth, 10 to the 13th diameter of solar system, 10 to the 16th is a light year, 10 to the 21st is the diameter of a galaxy. So the diameter of a galaxy is actually bigger than the amount of time or the amount of space that light can travel in an entire year. And then about 10 to the 5th times that diameter is the distance to the edge of the observable universe. So that is all of the length scales in meters. You can also look at masses in kilograms. Basically, the mass of proton is 10 to the negative 27th kilograms. Mass of electron is 10 to the negative 30th kilograms. So the mass of electron is 1,000, about 1,000 times less than the last mass of a proton. While the mass of the Earth is about 10 to the 25th times the mass of a liter of water, which is compared to the upper limit of the mass of the known universe by about 28 orders of magnitude. So 10 to the 28th is the distance, or is the change, or the times that the mass of the Earth can fit into the mass of the known universe, which is, massive. So time in seconds, mean lifetime of an unstable nucleus is 10 to the negative 22 seconds. 10 to the 0 seconds is 1 heartbeat, and the age of the universe is about 10 to the 18 seconds. So that's just kind of fascinating. Like, we talk about orders of magnitude because you have these massive differences in lengths, masses, and or time, based on different things that you're looking at. So we talk about orders of magnitude because we're talking about different scales of things, and the scales tend to scale logarithmically. So they scale times 10 to the whatever power rather than linearly. So the lifetime of an unstable nucleus isn't going to be about like a tenth of a heartbeat or anything like that. And then a heartbeat isn't going to be like a tenth of the universe. It's going to be differences in massive scales. It's going to be like 10 to the 18th times the time of 1 heartbeat is going to be the age of the universe. So that is why we have to talk about scientific method, or non-scientific method, or the scientific notation and orders of magnitude, because we are talking about these things that have massive orders of magnitude between them.